All right, Chem 1110 students, we are going to begin Chapter 12, which is the last chapter in our study of chemistry during this first semester. So we're looking at solids and liquids, and these are called condensed phases. And so the intermolecular forces that we talked about in the last couple of chapters, those attractive forces between the particles, are what hold them together in the condensed phase, and how strong they are determines whether it's a gas, liquid, or solid. And we have this picture sort of comparing gases, liquids, and solids. The gases, those molecules are moving around. They feel no attraction to the other particles in that container, whereas a liquid, the intermolecular forces are strong enough that they're close together, but not in any ordered fashion as seen in the solid, where the intermolecular forces are strong enough. Not only are the particles together, but they're together in a very ordered fashion. One of the properties is surface tension, and this is the amount of energy that's required to, stretch or increase the surface area of a liquid. And so this is directly proportional to the intermolecular forces. The stronger they are, the higher the surface tension, the more apt the liquid molecules are to stay next to each other. And here's a little diagram of that in a beaker. And here's an example of little rain droplets we see on the side of a car. You see them on, a mirror if you've taken a steamy shower. Water has a very high surface tension because it has very strong intermolecular forces, which of course are hydrogen bonding. So one of the effects of surface tension is capillary action. And capillary action is a movement of liquid up a narrow tube. It's a very strong movement, and in fact that's how water gets from the roots of, say, oak tree that's 60 feet tall up to its leaves. There are two types of forces that bring about capillary action. Cohesion, which is the attraction between the molecules, so that would directly be surface tension, and adhesion, and that's a surface or the attraction between the two different kinds of molecules, those in the liquid and those in the narrowed tube. And so we have an example here of comparing the capillary action in water, which is shown on the left, and it creates a meniscus. The adhesive forces are greater than the cohesive forces, so that water is very attracted to the silicon in the side of the glass. On the right-hand side, though, we have something like mercury, where the cohesive forces are much stronger than the adhesive forces, and so the top surface of that mercury is almost like a partial bubble. It does not climb up the glass at all. Another measure of or example of how intermolecular forces are important is viscosity. Viscosity is a measure of a fluid's resistance to flow. The higher the viscosity, the more slowly a liquid flows. And so, you can think of Karo syrup or pancake syrup. They're very slow to pour and have a much higher viscosity than, say, water or Coca-Cola. So materials that have a high viscosity also have very high intermolecular forces. An example here is glycerol. Glycerol is very thick and syrupy, and you can see the reason why. It's got 3 OH groups, which means there's a tremendous amount of hydrogen bonding between glycerol molecules. And here's an example of some other viscosities and their measurements. And so you have acetone and water are both very thin, very low viscosities, whereas that glycerol is a very high viscosity, over 1,000 times greater. Okay, now we're going to talk more about liquids, but in a little bit different way. We're going to look at the vapor pressure. This is also dependent on the intermolecular forces. So if you think about what vaporization is, it is because a molecule at the surface of a liquid gains enough kinetic energy, either by a change in temperature or by collisions with other molecules, that allow it to escape into the gas phase. That process is called vaporization. And there's always some distribution in the energy of various particles within a liquid. So this diagram on the left just shows you the number of molecules on the y-axis. Kinetic energy is on the x-axis, and so you can see the majority of the molecules have a very low kinetic energy, but the amount of kinetic energy necessary to escape the surface is marked as E1, and we've shaded the area under the curve to show you the number of molecules there would be that have enough energy to vaporize from a liquid. Now, if you have a higher temperature, which is shown on the right side, now that curve, that distribution of energies is spread out, and so you have more molecules at a higher temperature. There are more molecules that have enough kinetic energy to escape the surface. So vapor pressure increases until that rate of evaporation equals the rate of condensation. So in other words, you know, a liquid gas, a liquid sample of water, some of it's vaporizing to gas phase, but then some of those gas molecules hit the liquid again and stick. And so one is evaporation, of course, and the other is condensation. And you see we wrote it the same way with different direction arrows because we're going to start talking about equilibrium here. That's where the forward process equals the reverse process is called a dynamic equilibrium. And so you have a little diagram here that is a pressure indicator on the tube off the side of that cylinder. And so when it's frozen, you have empty space, you have no molecules in that space above it. You heat it up a little bit so that that becomes a liquid, and some of the gas molecules can escape, and that creates some pressure. So there's a differential in the height of that probably mercury that's in that U-tube. If you heat it up even more, the pressure increases. We get more gases in the the space above the liquid, and then that fourth picture is sort of showing you that some of those gas molecules are coming back, and so it's a dynamic equilibrium. All right, so the thing we need to recognize is that whenever things are at equilibrium, a glass of water that's sitting out overnight or ice cubes that are in a glass of water, you get this rate of evaporation equaling condensation, and this is just a little diagram to show you the two rates coming to be equal, because there is an equilibrium that is always going to exist between the vapor and the liquid phase. All right, we're going to look at properties of various liquids. We know they have different intermolecular forces, and so we're looking at the behavior of the liquid in terms of vapor phase versus temperature. As the temperature goes up, you see the vapor phase goes up, but diethyl ether, which is very volatile, as soon as you open a can of it, you can smell it. Lower intermolecular forces than water and a higher vapor phase, whereas mercury is very heavy and very little of it moves into the vapor phase. Nonetheless, in all cases, that vapor phase increases with temperature. Now we're going to look at some solids, and we're going to talk about melting points. So that's the temperature where the energies of the individual particles that are in this fixed solid are able to break loose of their fixed positions, and they can just sort of move over one another. We've seen this chart before because we have melting points versus the period in the periodic table. And what we see is that materials that are made up of things in that second period, so we're talking about the carbon, fluorine, nitrogen, oxygen, there's some anomalies, and that's because of the very high intermolecular actions, because those are very small molecules. The only one that seems to fit in the group is the methane, and that's because it has very low electronegativity. And here's just a list of some the types of intermolecular forces and the melting points, and you can see it varies by the mass and the type of intermolecular forces there are. We're going to look at vapor phase of solids. We have very few cases where molecules get enough energy to escape from a solid and go into the vapor phase. There's a few exceptions. Mothballs you can smell from across the room. There's iodine, which really is almost never a liquid. It goes from solid to vapor phase. And then we have dry ice on the right. Okay, another kind of solid form is an amorphous solid. It doesn't have a regular three-dimensional arrangement, and glass is an amorphous solid. If you visit a home that's extremely old, you'll see that the glass has sort of moved around and it looks wavy. Here's some examples of 3 different kinds of glass. Quartz glass is 100% silicon dioxide. Pyrex, which you can heat and cool, has some boron oxide and aluminum oxide in it. And then sodium lime glass is a kind, this is what we call cheap glass, and it's got silicon, sodium, and calcium in it, and you can see it's used in windows and in bottles. But it's all amorphous. It doesn't have a nice crystalline structure, and this quartz crystalline structure is generally seen as semi-precious stones. So these can be things like amethyst and citrine and emerald. All right, crystalline solids. True crystalline solids are very rigid and have a long range order, and they have a unit cell that repeats, and so here's an example. A cubic unit cell forms a bigger cube. Ionic crystals are very ordered because they are arranged by that attraction of the solid to the positive to the negative ions, and that unit cell is defined by how the positives and negatives line up. Here's 3 other ionic compounds and their unit cells. There are some solids that are purely covalent, and diamond is one of those, and you can see it's very rigid, whereas graphite, which is another form of carbon, has sheets of covalent structure. All right, looking at molecular crystals, we find that they're mainly held together by van der Waals forces, or hydrogen bonding can be one of those. So that's what we'd see for an ice cube. And metallic solids are very different because every part of the cell is an atom, and the electrons are just delocalized, which make them very good conductors of electricity. And here's just a table with